All right, so continuing our theme of non-traditional ferroelectric materials, our next speaker is an invited talk. Schroeder from NAM Lab in Dresden, Germany, will tell us a little bit about their ongoing work with hafnium oxide-based systems.
Okay, good morning, everybody. I hope you can hear me. So first of all, I'd like to thank the organizers for inviting me to this nice workshop. And it's for the first time for me to talk at a more fundamental physics audience. So far in the last 10 years, we had, well, mainly device conferences and a couple of material conferences. So be interested to get your feedback. So I'll introduce you to the hafnium oxide. And I heard last year there was a first talk on the topic. And the new part will be here also to look into non-polar regions of the hafnium oxide and how these impact then the ferroelectric switching of the hafnium. So I'll start with the hafnium oxide, compare the hafnium oxide to the PZT case, go a little bit through the two main devices where the hafnium oxide is currently used. And in industry, there's an enormous interest in the material because it's CMOS compatible and can be used directly right next to other devices on a chip. Then later on I will go into depolarization fields and discuss this in the content of wake-up cycling for the capacitor structure. Okay, so this is how we started basically with in 2006, when we were looking for a material for DRAM capacitors. At that time, only centrosymmetric phases for the hafnium oxide were known. So the pure hafnium oxide was in the monoclinic phase. And if you dope the hafnium oxide with certain dopants, you would have a tetracubic phase of the material. And at that time, in 2006-07, we found the orthorhombic phase of the hafnium oxide at this phase boundary between the monoclinic and the tetrahedral phase of the material. And this is how it looked like at that time. I was in a semiconductor company called Qimonda, who was doing DRAM, and you could see with different silicon content in hafnium oxide, there's certain features showing up which looked like ferroelectricity, and we went through lots of different steps to really prove that hafnium oxide was ferroelectric. So let's go in detail. For the silicon-doped hafnium oxide, what you could see is that the pure hafnium oxide, you had no remnant polarization, looks quite ferroelectric. The electric constant is 20, and you had mainly the monoclinic phase as the main phase for the hafnium oxide. Then if you increase the dopant content, you form this orthorhombic phase. You get a higher remnant polarization value, increased the electric constant, and you see that there's this orthorhombic phase here showing up in XRD. And when we went to higher silicon content, here you had this kind of pinched hysteresis shape related to the tetrahedral phase of the material. Again, here you see the drop of the remnant polarization value, a small decrease in the electric constant, and here the tetrahedral phase coming up. And yeah, you can put in more silicon and then properties disappear again. So there's a very small dopant range for this material, and in the order of like 1% where you can see the ferroelectric properties. And so we went through lots of different dopants, from very small dopants like silicon to really large dopants like lanthanum and strontium. And for all these dopants, we had this phase transition occurring. For the smaller dopants, we had also this tetrahedral phase, and for the larger dopants, we saw a direct transition into the cubic phase. And then, I'm sorry, the other possible material was a mixed hafnium zirconium oxide. And for this material, you see a much broader range where the ferroelectric properties are occurring. And since the crystallization temperature of this material is lower compared to the other doped hafnium oxide, this is currently the material used in most of the publications. How does this look like in a capacitor structure? So we typically form the material in between two tinitride electrodes, and then here you have your doped hafnium oxide layer. It's a polycrystalline material. The thickness of the grains is the physical thickness of the layer, and we typically are in the range between 5 and 20 nanometer for these films, and in the other direction we have a grain size in the order of 20 to 30 nanometer. And then if you look at, so this is about the tinitride grain size, so the hafnium oxide grains are roughly like a factor of 3 to 5 larger than what you see for the tinitride. Other things you can see, I mean, if your film is completely in the orthorhombic, in the ferroelectric phase of the material, there still seems to be certain regions with different crystal structure here. And we have also some orientational alignment between the tinitride substrate and the hafnium oxide grains in certain regions of the surface. So since the main topic of the talk is also non-polar regions in the film, where are non-polar regions? So if you look in the structure here, of course, since you have a nitride electrode and an oxide as the dielectric, if you deposit the film, you would expect that there's some interface reaction happening. And so we typically see, and this is what we hear in like 2 talks later, in XPS, that there's an oxidation of the tinitride, and we have some tioxide and tioxynitride portions in the layer at the interface. And if you look here with EBSD from top on the structure, you can see nicely here the hafnium oxide grains, and there are some mainly the larger grains which here show up as monoclinic grains. So it looks like that we have our polar orthorhombic phase grains, but that there are also non-polar regions which can have an impact then on the ferroelectric switching of our device. And the other thing, so if you look with TM at the interface between the tinitride and the hafnium oxide, you see here, for example, the tinitride, and here the orthorhombic phase of the material. In between, there's also a non-polar tetramer phase of the hafnium oxide right at the interface, quite likely coming from some defects in the hafnium oxide, which relate to then the different phase formation right at the interface. And with field cycling, so this is AC field cycling of your structure, these interfacial layers getting thinner. And that you have these non-polar phase portions, you can see also in piezo force microscopy, where you see a non-complete switching from one polarization to the other polarization orientation in some cases. In other cases, we can improve the films and it looks much better. The other thing you can see here, because we'll discuss this later, from the switching kinetics here in this work by Alex Ruverman, there is he tried to distinguish between nucleation limited and a chi switching behavior, and that he relates the switching here more to nucleation limited switching rather than to a chi model. Okay, now coming to the comparison to the PZT case. If we have here the perovskite structure for the PZT and here the hafnium oxide, here you can nicely see the 4 oxygen atoms responsible for the 2 polarization orientation of the hafnium oxide. And let's look first in what's common for the both materials. They both have a very similar Raman polarization value in the order of 20 to 30 microcoulomb per square centimeter. And in both cases, the Curie temperature is above 300 degrees C. So that's the reason why both materials can be used also for non-volatile memory application. And looking at the differences, the dielectric constant of the PZT is roughly a factor of 10 higher compared to the hafnium oxide. So we have here values in the order of 300 to 800 versus the hafnium oxide were more in the 30 to 40 range. And the coercive field, on the other hand, is instead of a factor of 10 higher, it's a factor of 10 lower compared to the hafnium oxide. So in hafnium oxide, we have about 1 megavolt per centimeter, and this is rather like 200 or 100 kilovolt per centimeter. And from the scaling, the PZT layers typically can be scaled down to 70 nanometer and below. You'll find dead layer effects resulting in depolarization effects of the material. And in the hafnium case, ferroelectric properties has been shown down to 5 nanometer and even below. And well, I mean, from this, the question comes, I mean, why is the same relation, I mean, why is the coercive field a factor of 10 lower in one case and the dielectric constant at the same time a factor of 10 higher? And we looked into textbooks and couldn't find any relation. And maybe, and this is what we kind of derive from Landau theory. And here you can see that if you have the Gibbs free energy and the two polarization states, then, well, you can derive this and switch P and E, and then you can see that the coercive field would be dE divided by dP, where this is 0, and then you can put this back into the calculation, and what you get out of this is that the coercive field would be related to 1 over K, and this is the dependence what you see for lots of different materials we looked into. But for some reason, we didn't see this somewhere in the textbook, and at least it looks some reasonable relationship and explanation for the high coercive field of the hafnium oxide. Looking to the switching kinetics, these are the typical models you find in literature, and we try to understand where is the hafnium oxide for these 3 different models. So in the Chi model, you kind of have a domain growth and coalescence of the grains. In the nucleation limited switching, you would have a different waiting time for nucleation related to the switching kinetics. And then in the Landau model, it would be, well, just coming from one polarization, overcoming the activation barrier and going to the other polarization orientation. And we looked into some of the properties of the hafnium oxide and compared them again to PZT. And so the first thing was that if you look at the coercive field and have a different mixture of the polar phase of the hafnium oxide and a non-polar phase in the same film, and the strange thing was that the coercive field is quite constant. And if you would expect like a Chi switching behavior, then if you would have a non-polar phase portion in your film, you wouldn't expect that you could have some domain growth and coalescence of the grains. So we think due to this quite constant coercive field in this very wide range of different compositions of the film, we think that we don't have a Chi model, and that's what you could see already in the PFM measurement I showed you before. The other thing is that if you're looking to the thickness dependence of the hafnium oxide, you see a really broad range even for epitaxial grown hafnium oxide film, where you have a coercive field in the order of roughly a little bit above 1 megavolt per centimeter, and only for the very thin films below 10 nanometer, the coercive field is going up. But I'll show you later, we think this is coming from some depolarization effects. But this is definitely different compared to the PZT case or other perovskites where you have this relation to d over 2 minus 2 third for the switching kinetics and the relation to the coercive field. And so from this different thickness dependence, we think that also the nucleation limited switching behavior is not a good explanation for what we see for the switching kinetics. And you can also, I mean, these are the typical relations of the switching time versus the field in the three different models. And you can see, I mean, we checked this, I mean, basically everything fits. So we kind of needed well, look a little bit closer and decide on what's the switching model, and that's why we went through this procedure on the slide before. And so the one thing why we think the hafnium oxide is different compared to other materials is hafnium oxide has an extremely small grain size compared to the other cases. We're always in the order of 10 to 20 nanometer and maybe 30 nanometer in most of the measurements. And we think that these grains have a lot of defects at the outside of the grains, which means that quite likely the switching behavior of these grains happen from one grain without knowing what's happening in the next grain. And that this kind of explains this Landau type switching. Okay, now coming to the devices. So this is one of the devices you find at device conferences. Basically, you have in a memory cell the capacitor, where you can store your information, and the transistor for selecting your information. And so the main important thing you need for these capacitors that they can switch a lot of time. So what industry is looking for is like 10 to 15 times without any major degradation. And in the PZT case, you could see in the beginning when platinum electrodes were used, this wasn't the case, but once the oxide electrodes were introduced, you could reach now in devices, you can buy something like 10 to 15 cycles before you see a degradation of the device. In the hafnium oxide, since we have the tinitride electrodes, so far we don't reach the numbers, but you see already quite stable switching behavior up to 10 to 10 cycle. Well, here's a fatigue behavior, and there's a slight wake-up behavior for these devices. But industry is already quite, well, looks like very promising for the application. And the one thing we just lately introduced this into a 16K memory array. And here you can see, well, this was the behavior on the larger structure. As I showed you before, we could show that even if we just anneal the hafnium oxide to 350 degrees C, we can have nice remnant polarization values. And if you put this in a very small 600 nanometer capacitor structure, that you even get nice linear cycling behavior up to 10 to 11 cycles. And this was just the end of the measurement, and they didn't have any longer measurement time available here. So switching speeds in the order of 30 nanometers, operation voltage at 2 volt, and endurance beyond 10 to 11 cycles. This is what's making this interesting for industry applications. And the other application is the transistor. And then here in this case, you just take a normal transistor, just replace your normal dielectric in the transistor structure by a ferroelectric material, and depending on the polarization orientation of your device, you're changing the channel in the transistor, and basically you're changing your turn on voltage, your threshold voltage of your transistor structure. And you can see here, depending on the two polarization orientation you have here, like 1 volt difference in the threshold voltage. And these are the current devices as done at Global Foundries. They're like 28 nanometer size structures. And if you have a top view of these structures, you can see they consist of just 3 grains. So you have just 3 grains in there. Well, since the talk is about depolarization fields and impact of these non-polar phase regions, one non-polar phase is here at the interface between the hafnium oxide and the substrate, because there's always a silicon oxide there which is non-polar, or it could be that one of these grains is non-polar, and this can have also some impact on your devices. Overall switching behavior, you can switch it to 10 to 6 times, and due to these interfacial layers you get trapping, and then the devices don't break, but the memory window gets smaller. Okay, so this was the small detour into the device area. Now coming back, so we looked into what can these non-polar phase portions do. And so there were 2 models we tried to apply. So one is finite screening here. And you can see here when we have the depolarization field that we don't have a complete or the screening charge right next to the dipole, and you get your potential and the E field. And you can calculate depolarization fields and screening charge. And if you look at the depolarization field, then you can see here for films which are smaller than 10 nanometer that these depolarization fields, even if they're really small, can be larger than the coercive field and cause some relaxation effects. And in the second model, we included a dead layer in between our ferroelectric material and the electrode. And well, you can again calculate depolarization fields and interface fields, which are important for charge injection into these interfacial layers. And again, you see that the depolarization fields are quite large. Again, for these thin films getting above the coercive field of the material, but they're very similar to the PZT case. And the main difference between the hafnium oxide and the PZT case is that the hafnium oxide is proposed to be used in this 10 nanometer range where depolarization fields are high, but the PZT, when you look at memory devices, is rather in the 70 nanometer range where depolarization fields are smaller. And so with this model, you can also look into what effect do you have if you measure your polarization hysteresis. And if you have like a 200 nanometer thick film, you won't see something of these interfacial layers. But if you're decreasing your film thickness and below 10 nanometer, these hysteresis start to pinch. And then if you look at basically the coercive field for final switching to the opposite polarization orientation, you can see that it's going up. And this is why we think that we see this impact here for the very thin films to higher coercive fields. And this is how this looks in experiment. Like here's silicon doped hafnium oxide. You can see nice hysteresis, and then for higher silicon content, how this pinching of the hysteresis loop occurs. And the other material I like to show you would be here the hafnium zirconium oxide. Again, you get from a normal hysteresis to a pinched hysteresis curve. And so we think the pure zirconium oxide still has, and that's also what we find in XRD measurements, the pure zirconium oxide has probably something like 20% still of the orthorhombic phase in the material. And you would have to add, and that's what you find already in literature, add some like yttrium to the zirconium oxide, like yttrium stabilized zirconium oxide, to really get the material tetragonal and not ferroelectric anymore for these thin films. Okay, quickly, wake-up behavior. So that's where you should see this effect. We prepared some samples where we have a defined interfacial layer with different aluminum oxide thickness, which is a non-polar layer. And well, what do you expect from this cycling behavior? Well, you see what I explained, from a pinch to a nice hysteresis loop. And as possible causes, you have either depinning of domains, and the other thing which was discussed so far was a phase transition from a non-polar to a polar phase of the material. And well, for all these cases, we measured this effect of a deep pinching of the hysteresis loop. And if you look at how remiporization changes with cycling, you can see this was the case without any aluminum oxide layer. And if you increase the aluminum oxide thickness, you see a drastic decrease of the initial remiporization value, and then also a strong wake-up behavior just coming from these interfacial layers. And so we just looked into a typical conventional wake-up effect should be just linear, and you wouldn't expect some behavior like here in the red case. And so we did a detailed study on the switching and like how switching peaks were basically changing and impacted by this. And so overall we came to the overall model that we think in the first phase we still have this deep pinning. Then the second phase we think we have a injection of charges in this interfacial layer, which reduces the depolarization field over time. And then in the third phase, we have like also injection. So first injection only in the interface, and then later on also injection into the bulk of the hafnium oxide, which then degrades the properties later on. So with this, I'd like to come to the summary, and I hope I could give you some nice overview of what we think, how hafnium oxide works, and how it compares to the PZT case, and that we have in hafnium oxide, since we have really thin films, a much stronger effect of nonpolar phase portions in the layer, and with this much stronger depolarization field compared to the PZT case, and these cause these wake-up effects. And something I didn't show, like retention issues, and that especially if you want to use this for devices that which have a strong interfacial layer, like a transistor case, that this will be challenging. And I'd like to thank you for your attention, and all the group members working on the topic, and thank you very much.
All right, any questions? All right, I'm going to take chair's prerogative. I'm taking the first one. So there's a big push for low voltage, low power operation. And this is one of the concerns I have about the hafnium oxide system, is that because the coercive fields are so large, even when you scale it down, we're still talking close to about a volt. Do you guys see a pathway forward in this kind of 100 millivolt kind of push? There's a lot of talk in some of the other fields pushing towards 100 millivolt operation for these devices. Do you think there's a chance for the hafnium in that case?
Well, that's why we were looking into where is this high coercive field coming from, and that's why maybe the thing is, if we could increase the electric constant of the hafnium oxide, maybe by certain doping, that we also can reduce the coercive field, and this is our current hope, that we can also reduce the coercive field overall.
Thanks. I'd like to ask what is known about domain walls, if they play any role in switching.
Well,
is there any experimental evidence for domain walls?
The thing is, again, the small grain size, and typically domain walls are seen like with PFM, and since the grain size is in the order of 10 to 20 nanometer, it's really difficult to see something which is smaller than these grains in PFM. And if you look at most of the studies currently you find in literature, it looks like there's, single grains are switching, but since you can't look at this small scale, I mean, PFM typically has like in the 100, 200 nanometer scale, you see probably that you have more and more grains are switching, and it looks like, this coalescence of multi-grains rather than some domain walls which are moving over the surface. This would be my current view on the topic. Probably we have to look a bit deeper into the topic and
yeah, it's probably related to the this absence of the K-Dunn law in coercive field versus distance. Thanks.
Has to be very quick.
Really quick. So when you have this pinching, when you go to thinner and thinner films, that looks like an antiferroelectric. So that kind of, those figures you have shown, the modeling you have done, does it suggest that you stabilize an antiferroelectric phase of hafnia when you go very thin?
Well, I mean, this is the main discussion before we looked into this depolarization field was, do we have a field-induced phase change of maybe the tetrahedral, non-polar tetrahedral phase into the orthorhombic phase? This is what we thought before, and there are also some indications that there are some field-induced effects. I saw some TM studies coming up. But the question is how to distinguish between depolarization fields and possible phase changes with field. So probably we have to look a little bit more in the topic to really understand what's happening here. Yeah. But it's probably nothing like you have two phase orientations which are then becoming sort of standard anti-ferroelectric materials or so.
All right, let's thank our speaker one more time. Do you need a there's one here too. I think you can use that one. Just to make sure it works. Yeah.
There's a switch on the top to turn it on. And it should turn green.
That's it.
Hello.